In the last video, we set out to find the eigenvalues of this 3 by 3 matrix A. And we said, look, an eigenvalue is any value lambda that satisfies this equation if V is a non-zero vector. And that says, well, that means any value lambda that satisfies this equation for V is not a non-zero vector. We just did a little bit of vector, I guess you could call it vector algebra up here to come up with that. You can review that video if you like. And then we determined, look, the only way that this is going to have a non-zero solution is if this matrix has a non-trivial null space, and only non-invertible matrices have a non-trivial null space, or only matrices that have a determinant of 0 have non-trivial null spaces. So you do that, you got your characteristic polynomial, and we were able to solve it, and we got our eigenvalues where lambda is equal to 3 and lambda is equal to -3. So now let's do what I consider the more interesting part, is actually find out the eigenvectors or the eigenspaces. So we can go back to this equation. For any eigenvalue, this must be true. This must be true, but this is easier to work with. And so this matrix right here times your eigenvector must be equal to 0 for any given eigenvalue. This matrix right here, I just copied and pasted from above. I marked it up with the rule of Cyrus, but you could ignore those lines. It's just this matrix right here for any lambda. Lambda times the identity matrix minus A ends up being this. So let's take this matrix for each of our lambdas and then solve for our eigenvectors or our eigenspaces. So let's take the case of lambda is equal to 3 first. So if lambda is equal to 3, this matrix becomes lambda plus 1 is 4, lambda minus 2 is 1, lambda minus 2 is 1. And then all of the other terms stay the same. Minus 2, minus 2, minus 2, 1, minus 2, and 1. And then this times that vector v, or our eigenvector v, is equal to 0. Or we could say that the eigenspace for the eigenvalue 3 is the null space of this matrix, which is not this matrix. It's lambda times identity minus A. So the null space of this matrix is the eigenspace. So all of the values that satisfy this make up the eigenvectors of the eigenspace of lambda is equal to 3. So let's just solve for this. So the null space of this guy is, we could just put in reduced row echelon form. The null space of this guy is the same thing as the null space of this guy in reduced row echelon form. So let's put it in reduced row echelon form. So the first thing I want to do, let me just do it down here. So I'll keep my first row the same for now. 4, minus 2, minus 2. And let me replace my second row with my second row times 2 plus my first row. So minus 2 times 2 plus 1 is 0. 1 times 2 plus minus 2 is 0. 1 times 2 plus minus 2 is 0. This row is the same as this row, so I'm going to do the same thing. Minus 2 times 2 plus 4 is 0. 1 times 2 plus 2 is 0. And then 1 times 2 plus minus 2 is 0. So the solutions to this equation are the same as the solutions to this equation. Let me write it like this. Instead of just writing the vector v, let me write it out. So v1, v2, v3 are going to be equal to the 0 vector, 0, 0, just rewriting it slightly different. And so these two rows, or these two equations, give us no information. The only one is this row up here, which tells us that 4 times v1 minus 2 times v2, actually this wasn't complete reduced row echelon form, but it's close enough, it's easy for us to work with. 4 times v1 minus 2 times v2 minus 2 times v3 is equal to 0. And, well, let's just divide by 4. I could have just divided by 4 here, which might have made it, maybe I skipped a step. But if you divide by 4, you get v1 minus 1/2 v2 minus 1/2 v3 is equal to 0. Or v1 is equal to 1/2 v2 plus 1/2 v3. Just added these guys to both sides of the equation. Or we could say, if we say that, let's say that v2 is equal to, I don't know, it's equal to, I'm just going to put some random number a, and v3 is equal to b, then we can say, and then v1 would be equal to 1/2 a plus 1/2 b, we can say that the eigenspace for lambda is equal to 3 is the set of all vectors v1, v2, v3 that are equal to a times v2 is a, right? So v2 is equal to a times 1. v3 has no a in it, so it's a times 0. I'll say v1 plus b times v2 is just a, right? v2 has no b in it, so it's 0. v3 is 1 times, so 0 times a plus 1 times b. And then v1 is 1 half a plus 1 half b. 1 half and 1 half. For any a and b, I could, such that a and b are members of the reals, just to be a little bit formal about it. So that's our any vector that satisfies this is an eigenvector, and they're the eigenvectors that correspond to the eigenvalue lambda is equal to 3. So if you apply the matrix transformation to any of these vectors, you're just going to scale them up by 3. Or you could say, let me write it this way. The eigenspace for lambda is equal to 3 is equal to the span, all of the potential linear combinations of this guy and that guy. So 1 half, 1, 0, and 1 half, 0, 1. So that's only one of the eigenspaces. That's the one that corresponds to lambda is equal to 3. Let's do the one that corresponds to lambda is equal to minus 3. So if lambda is equal to minus 3, I'll do it up here. I think I'll have enough space. Lambda is equal to minus 3. This matrix becomes, I'll do the diagonals. Minus 3 plus 1 is minus 2. Minus 3 minus 2 is minus 5. Minus 3 minus 2 is minus 5. And then all the other things don't change. Minus 2, minus 2, 1, minus 2, minus 2, and 1. And then that times vectors in the eigenspace that corresponds to lambda is equal to minus 3 is going to be equal to 0. I'm just applying this equation right here, which we just derived from that one over there. So we're looking, the eigenspace that corresponds to lambda is equal to minus 3 is the null space of this matrix right here, or all the vectors that satisfy this equation. So what is the null space of this is the same thing as the null space of this in reduced row echelon form. So let's put it in reduced row echelon form. So the first thing I want to do, I'm going to keep my first row the same. I'm going to write a little bit smaller than I normally do, just because I think I'm going to run out of space. So minus 2, minus 2, minus 2. And then, actually, let me just do it this way. I will skip some steps. Let's just divide the first row by minus 2. So we get 1, 1, 1. And then let's replace this second row with the second row plus this version of the first row. So this guy plus that guy is 0. Minus 5 plus minus, or let me say it this way. Let me replace it with the first row minus the second row. So minus 2 minus minus 2 is 0. Minus 2 minus minus 5 is plus 3. And then minus 2 minus 1 is minus 3. Minus 3, and let me do the last row. I'll just do a different color for fun. And I'll do the same thing. I'll do this row minus this row. So minus 2 minus minus 2 is 0. Minus 2 plus 2. Minus 2 minus 1 is minus 3. And then we have minus 2 minus minus 5. So that's minus 2 plus 5, so that is 3. Now let me replace and I'll do it in 2 steps. So this is 1, 1, 1. I'll just keep it like that. And actually, well, yeah, let me just keep it like that. And then let me replace my third row with my third row plus my second row. It'll just zero out. You just add these terms. These all just become 0. That guy got zeroed out. And let me take my second row and divide it by 3. So this becomes 0, 1, minus 1. And then I'm almost there. I'll do it in orange. So let me replace my first row with my first row minus my second row. So this becomes 1, 0. And then 1 minus minus 1 is 2. 1 minus minus 1 is 2. And then the second row is 0, 1, minus 1. And then the last row is 0, 0, 0. So any v that satisfies this equation will also satisfy this guy. If it's in this guy's null space, it's going to be in the null space of that guy in reduced row echelon form. So v1, v2, v3 is equal to 0, 0, 0. And let me move this because I've officially run out of space. So let me move this lower down where I have some free real estate. So let me move it down here. This corresponds to lambda is equal to minus 3. This was lambda is equal to minus 3, just to make us, it's not related to this stuff right here. So what are all of the v1s, v2s, and v3s that satisfy this? So if we say that v3, let's say that v3 is equal to t. If v3 is equal to t, then what do we have here? This tells us that v2 minus v3 is equal to 0. So it tells us that v2 minus v3, right? v2 is 0 times v1 plus v2 minus v3 is equal to 0, or that v2 is equal to v3, which is equal to t. That's what that second equation tells us. And then the third equation tells us, or the top equation tells us v1 times 1. So v1 plus 0 times v2 plus 2 times v3 plus 2 times v3 is equal to 0. Or v1 is equal to minus 2 v3, which is equal to minus 2 times t. So the eigenspace that corresponds to lambda is equal to minus 3 is equal to the set of all the vectors v1, v2, and v3, where, well, it's equal to t times v3 is just t, right? v3 was just t. v2 also just ends up being t, so 1 times t, and v1 is minus 2 times t, for t is any real number. Or another way to say it is that the eigenspace for lambda is equal to minus 3 is equal to the span. For lambda, I wrote this really messy. For lambda is equal to minus 3 is equal to the span of the vector minus 2, 1, and 1. Just like that. And it looks interesting because if you take this guy and dot it with either of these guys, I think you get 0. Is that definitely the case? If you take minus 2 times 1/2, you get a minus 1 there, and then you have a plus 1, that's 0. And then minus 2 times 1/2, yeah, you dot it with either of these guys, you get 0. So this line is orthogonal to that plane. Very interesting. So let's just graph it just so we have a good visualization of what we're doing. So, we had that 3 by 3 matrix A. It represents some transformation in R3. And it has 2 eigenvalues, and each of those have a corresponding eigenspace. So the eigenspace that corresponds to the eigenvalue 3 is a plane in R3. It's a plane in R3. So this is the eigenspace for lambda is equal to 3. And it's the span of these two vectors right there. So, if I draw, maybe they're like that, just like that. And then the eigenspace for lambda is equal to minus 3 is a line. It's a line that's perpendicular to this plane. It's a line like that. It's the span of this guy. Maybe if I draw that vector might look something like this. And it's the span of that guy. So what this tells us, this right here is the eigenspace for lambda is equal to minus 3. So what that tells us, just to make sure we are interpreting our eigenvalues and eigenspaces correctly, is look, you give me any eigenvector, you give me any vector in this, you give me any vector right here, let's say that is vector x. If I apply the transformation, if I multiply it by a, I'm going to have 3 times that because it's in the eigenspace for lambda is equal to 3. So if I were to apply a times x would be just 3 times that. So that would be a times x. That's what it tells me. This would be true for any of these guys. If this was x, and you took a times x, it's going to be 3 times as long. Now, these guys over here, if you have some vector in this eigenspace that corresponds to lambda is equal to 3, and you apply the transformation, let's say that this is x right there. If you took the transformation of x, it's going to make it 3 times longer and in the opposite direction. It's still going to be on this line, but just in So it's going to go down like this, and that would be a times x. It'd be the same. It'd be 3 times this length, but in the opposite direction, because it corresponds to lambda is equal to -3. So anyway, we've, I think, made a great achievement. We've not only figured out the eigenvalues for a 3 by 3 matrix, we now have figured out all of the eigenvectors, which are, there's an infinite number, but they represent 2 eigenspaces that correspond to those 2 eigenvalues for -3 and 3. See you in the next video.